Hello team, this is section 6.3. We are moving on in linear growing patterns, composite rules. It's an extension of 6.2 section, and really it's the same thing, it's just kind of pushing it up a little in terms of difficulty. So if you look at the introduction in terms of notes, it says the same things that it says 6.2. We're looking at composite linear patterns. There's two parts that we're going to be able to derive from there. So we're going to be able to derive the multiplier and the constant. So there's the multiplying part and the adding part. So remember, we call the multiplying part the multiplier, adding part is the constant, it's the number of blocks that stays the same all the time, and the multiplier is the number of blocks that the pattern increases by. So the only difference now is that when we're looking at these visual representations, all the blocks are the same. So there's no black tiles, there's no gray tiles, there's no shaded, there's no different patterns. They're all, in this case, they're all square tiles, and there's just no difference in them. We can still see some, which tiles are going to stay the same constant and which ones are changing, but I'm going to show you a few ways that's going to work all the time, no matter what kind of blocks you have or what kind of situation you have. Ultimately, we are creating pattern rules, which is something like this, and we're going to use that to make some predictions. All right, I'm going to well, I guess I can go over the example. So in the example, what they have is they have a visual representation of tiles over here, and we have to find a multiplier part and we have to find a constant part. If you look at the visual representation, you can see that there are two of these tiles that kind of stay the same all the way throughout. So that's going to be our constant, and that's why they have an answer for the constant is just +2. And then you can see that in position 1, you start with 5 of these tiles, and then you increase by another 5 and another 5. So not 3, just 5. So that is going to be our multiplier. And that's why they have times 5 here, or 5x plus 2. There we go. I'm going to show you a different way than what they've done here in our first example, I believe. Yeah, there we go. So it's another one of those comparison ones. We have visual representation, we have a pattern rule given to us, which is y equals 6x plus 5, and we have to confirm that they are really the same. That this pattern rule represents the visual representation. I'm going to expand it a little more because I'm going to show you some really the skills to kind of create the pattern rule from the visual representation that we have here, and I'm going to draw upon what I said in section 6.2. So let's look at it. We have a bunch of tiles. We have 3 positions. In the first position, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I'm going to write here, there's 11 tiles. Okay, in the next one, there's 2, 4, 6, 8, 10, 12, 14, 16, 17. All right. And in this one, we have, it's, what is it, 6 across, 6 times 3, 18, 21, and then 23. Okay, let's see if that works. So now we ask ourselves, what is the increase? What is the pattern? What's happening here? So it seems like in position 1 there's 11, and then we're adding 6, and then we're adding 6 again. Okay, so our multiplier is going to be 6. So right now I know that I can create an equation as y equals 6x. I need that constant, so plus something. In section 6.2, I said the easiest way to find a constant is to actually find the 0th position. How many tiles do you have in the 0th position? So I'm going to use that here. Here's my 0th position. And because I am increasing by 6 if I go to the right, I'm going to subtract by 6 because I'm going backwards to the 0th position. So 11 minus 6 is going to be 5. So that means that there's 5 tiles, and that is what represents our constant. So in this case, it's y equals 6x plus 5. And that's going to be our pattern rule for this visual representation. And at the same time, it is what they've offered us here. And so we can justify that, yes, this pattern rule does describe the visual pattern. All right, moving on to the next question. It says, given the pattern rule, number of tiles equals position number times 3 plus 2, or y equals 3x plus 2. Draw a visual representation for our first three positions. All right, so visual representation, 1, 2, 3. If you remember from 6.2, because it's pretty much the same, we can determine the position numbers just by substituting 1 instead of the x, and that's going to give me the value for position 1. So in this case, it's going to be y equals 3 times 1 plus 2. 3 times 1 is 3 plus 2 is 5. So that means at the beginning, there's going to be 5. There we go, 5 tiles. And the next one, we can just follow up with the same thing. Y equals 3 times 2 plus 2. I'm just going to fix that. 3 times 2 is 6 plus 2 is 8. There we go. So in this one, let's see how I can do that. 1, 2, 3, 4, 5. And then I need 3 more. So maybe something like this. There we go. And then I will do the same thing again. Now, once I found the first one, I know because of the multiplier 3 times x, I know that it's going to be increasing by 3. So plus 3, plus 3. So now I don't really have to do the substitution. I can just add 3 to where I already have. I have 8 in this one, so plus 3 is just going to be 11. And I'm just thinking, how am I going to sketch that? So I think I'm going to do 5. There we go, and split them into 2, and that's going to give me 10, and then just one more. Something like this. You can be a little fancier, kind of what they did up here in the sample and make like a little pyramid, but I just stuck with this. You can also kind of indicate that the constant is 2, so you can just kind of have 2 at a time and increase 2 at the bottom that are not changing, and then change the top ones, but I just prefer this way. Next question. So Seif is making stacks of $1 coins. There they are over here. And determine a pattern rule to represent his stack of coins. So there we go. So we're going to apply what we did in first example, where we have 3 positions, 1, 2, 3, 4, 5, 6, 7 coins, and then it seems like there's 2 more, so this is going to be 9, and obviously this is going to be 11 if it's 2 more. So you can see that it's increasing by 2 from one stack to another, so that means that our pattern rule is going to be y equals 2x, because our multiplier is that increasing number. And again, super easy. If you go backwards, find a position number, that means subtract 2. I'm just going to write 5. There's going to be 5 coins there, which means it's going to be plus 5. That is my constant. So this is the pattern rule. And we can use that pattern rule now to estimate what's going to happen in stack 4. You can use like I said, the pattern rule just by substituting. So I'll do that. 2 times 4 plus 5. There we go. 2 times 4 is 8 plus 5 is going to be 13. Or another way is we can just continue from this stack over here and just add 2 more, which would be 11 plus 2, and that's also 13. So there's a few ways of doing this. Obviously, this position, the stack number 4, it's a low number. If it was, stack number 100, I would definitely just use the equation or a pattern rule. All right, next question, very similar again to 6.2. This is substitution. We're inputting a certain value for positions, so positions are represented by x, and then we're just punching it in a calculator. So we have position 4, 10, and 100. And first pattern rule is y equals 10x plus 12. So you can see that 10 is the multiplier, which means that whatever this pattern is, it's increasing by 10 from position 1 to 2, and then by 10 from position 2 to 3, and so on and so on. But the constant is 12. It stays the same with 12 of these tiles, let's say we're talking about still. So all I'm going to do is I'm going to substitute I'm going to take a 10 times 4, which is my first position, and then plus 12. And you can multiply it. 10 times 4 is 40, plus 12 is going to be 52. And if you don't have a if you have a calculator, just punch it in. So 52. And I'm going to do the same thing for the next position. So I'll write that 52 here. 10 times 10. There we go. Plus 12. 10 times 10 is 100. Plus 12 is going to be 112. There we go. And same thing here. 10 times 100, which is 1,000, plus 12 is going to be 1,012. There we go. So we've seen that in the first one, there's a pattern rule given to us. In the second one, it's a visual representation, so it would be useful to create our pattern rule and then use that to determine the number of tiles in certain positions. And we're going to do the same thing for C because we have a table of values given to us, so we're going to follow the same process. So again, I'm going to count how many tiles I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in this one. And then it's really bad quality. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, I believe. Your picture should actually... I have the textbook here, so maybe I should count there so I can get more exact. And then we have 4 and 3 is 7, 11, 14, 18, 21, 23, and 26. So it looks like this next one is 26, if I counted everything right. All right, so it goes from 12 to 19. That's a jump in 7, so plus 7. There we go. And then from 19 to 26 is also plus 7. That means their pattern rule is at least 7x. And if we're working backwards to find the constant, the part that's not changing, I'm just going to subtract 7. And in this case, it's going to be that there's only 5 tiles. Oops. I should fix that. There we go, 5 tiles. So that means it's going to be 7x plus 5. Once I have this pattern rule, all I have to do is do the same thing that I did with part A and substitute position 4, 10, and 7, and 100. So I'm going to do that over here. Y equals 7 times 4 and plus 5. And y equals 7 times 10 plus 5. And y equals 7 times 100 plus 5. There we go. So 7 times 4 is 28, plus 5 is going to be 33. 7 times 10 is 70, plus 5 is 75, and 7 times 100 is 700, and plus 5 is 705. So those are our number of tiles in position 4, 10, and 100. There we go. And the last one, table of values, same process, but I actually find it a little bit easier because tiles are counted for us. So all we have to see, okay, 23 minus 12, and if you remember, that was first differences. We had to subtract 23 minus 12, and that would give us what the first differences are. In this case, it's 11. And then we slide down and we see what the next first difference is, next value, 34 minus 23, that's also 11. All right, so it seems like it's number of tiles is increasing by 11, which means it's going to be, the pattern rule is going to be 11x. And if you want to find what the constant value is, just go backwards. I'm going to put, this is going to be my 0. So I'm going to subtract 11, and I'm going to get that the constant is 1. There we go, so plus 1. And that's it. Same process again. Substitute, so y equals 11 times 4 plus 1, 11 times 10 plus 1, and 11 times 100 plus 1. There we go. So 11 times 4 is 40. 4 plus 1 is going to be 45. 11 times 10 is 110. Plus 1 is 111. And 11 times 100 is 1100. And plus 1 is 1101. There we go. So that's our number of tiles for position 4, 10, and 1 and 100. There we go. So we had three different patterns represented in three different ways, and we either had a pattern rule or we created pattern rules, and then we just used simple substitution. For number 5, it says create your own pattern rule that includes multiplier and a constant, draw a visual, and create a table of values, and then predict the number. So I'm going to do an example. You guys can do a separate one. So let's say my multiplier is going to be 2, and my constant is going to be 3. I'll keep it simple. I'm just going to erase these dots. So draw visual representation. That means that in the first position, so here's my first position, second, and third. If I substitute 1 in here, so what I mean by this is y equals 2 times 1 plus 3. I'm going to get 5. That means in the first position there's going to be 5. In the table of values, I can do the same thing and I can record 5 right away. What am I going to do? I guess I'm going to do just square tiles. I mean rectangular tiles. Or square. Maybe they're squarish. They're not perfect. So that's 5. The second thing is I can go and substitute 2 for my second position, but I know that its number of tiles is going to increase by 2. So if I have 5 here, I'm going to have 7 in the next one. So 5 and 2 more. There we go. And then again, plus 2. So here is plus 2. And at the same time, I'm going to enter in table of values because that's my number of tiles. And then plus 2 over here. There we go. I'll have 5 at the bottom. 2 from before, which is 7. And then 2 more is going to bring us to 9. And I'm going to enter that in the table of values. So we kind of did this at the same time. Uh, and you can do that as well, depending on these questions. And the last one, it says predict the number of tiles needed to build position 5 and 75 for your pattern. So again, I'm just going to use a simple substitution. Our pattern rule was 2x plus 3, and I'm going to substitute 2 times 5 plus 3, and I'm also going to substitute 2 times 75 plus 3. There we go. So 2 times 5 is 10 plus 3 is 13. So there's going to be 13 tiles in position 5. And 2 times 75 is 150 plus 3 is 153. There's going to be 153 tiles in position 75. So if you go all the way down the line and draw number 4 and so on and so on, when you hit 75 there's going to be 153 tiles, which is a lot. That's why we don't draw it.